important is that they're independent. So you can think about it this way. As we're given samples from this type of model where we observe many of these, y variables, and what we want to do is we want to find a change of basis, a linear one, which makes the variables as independent as possible. So we want to decouple the dependencies between these different entries in y. So that's the basic problem. So I'll get back into, there are some assumptions that we're going to make beyond this, which I'll get into in a second. But first, let me tell you about one of the, applications. So it has lots of applications in signal processing. Maybe one of the most famous ones is what's called the cocktail party problem. So here's the setup. So there are n conversations going on in the room, and we have n microphones. And the idea is that each microphone hears a superposition of the conversations. And the key question is, can we disentangle them? So you can think about it in this way, that this matrix A is, each of the entries in X, first of all, represent the different conversations, what the corresponding amplitude is. And then we can think about A as being some matrix which describes for each microphone how it's influenced by the different conversations. So there are a lot of assumptions that go into sort of thinking about these two problems even in the same ballpark. But the sort of key idea is that the conversations are independent, so they're going on independently. And that when you think about measuring them at periodic time intervals that are far enough apart, that they're fresh samples from this model every time. So the idea is, can you actually reconstruct what this mixing matrix is that describes how the different conversations aggregate at each different microphone? So this problem was defined a long time ago in maybe the 80s. But I think by now we can come up with better names. So henceforth, I'm going to rename it. And this is forever what it'll be called. I'll change the notes to reflect this fact. But whenever anyone tells you about the cocktail party problem, you should call it this instead. Let's call it the MSA problem. All right, but the abstraction we're going to do is through ICA. So this is one of the applications. Sometimes you'll also hear this called blind source deconvolution. There are a few different formulations for this question, but ICA is a popular approach to doing it. So, but back to the model, right? So this is the setup we're interested in. We have this unknown A and B, and we get samples in this model where the coordinates are independent. Now, there's some natural things which don't really change the model. So, what we're going to do is we're going to assume that each of the coordinates, xi, has mean 0, because otherwise I could pull out whatever its mean is, correct it, and shift it into the b vector itself. So that's not a big deal. The other thing that I'm going to do is I'm going to assume that all of the second moments are 1. And the final thing that I'm going to assume, which you don't necessarily need to assume, is that A has full rank. So we'll assume it's an n by n matrix, but there's a lot of work on understanding what happens when it has fewer rows than columns, when you have fewer observations than variables, that you can still do interesting things in that setting. But the same way that we're going to work with just fourth order moments, if you go to higher order moments, you actually can work with fewer observations than variables under other sorts of conditions. But these are the types of assumptions we'll be interested in. These two assumptions are really not a big deal for the reasons that I described, because I can always change my model to reflect this assumption just by pulling out the mean or by rescaling the different columns of A. So these are not really a big deal. Right? And so under these types of conditions, the best I can hope to do is I can hope to recover the columns of A, but up to sign flip and up to permutation. Because the same way if I change one of the columns in A to minus that column, I can shift whatever the distribution is and flip it too and preserve the fact that I'm getting samples from exactly the same model. The same way that when I permute the columns of A, I can also apply the same permutation to the variables, to the entries in X, and obtain, again, the same exact distribution. So our goal really is to recover A up to sign flips and permutations and to recover B from this type of model under this really critical assumption that the components are independent. So are there any questions about this goal? And we're going to do it through the method of moments.
So, Anchor, when you say that the coordinates X are independent, I'm not quite sure if I understand what you mean. I know what rows or columns are independent, but coordinates, like every coordinate, they're already
This
different.
is a random variable.
Okay, I got it. I got it now, basically.
Okay. All right, good. Yeah. All right, so that's the main goal. The other thing I want to mention is that what's a little bit less obvious from this is that there are certain types of distributions which for other reasons are nice. Usually you think about the Gaussian distribution as being the natural, nice distribution. But in this setting, you really can't do anything when it's Gaussian. So that's actually the other assumption that you have to make, and that really is a critical thing. It's because the Gaussian has all sorts of spherical symmetries to it. So in that way, you'd never be able to recover A beyond modulo this rotation that you'd never be able to figure out, even information theoretically. So what I want to talk about first is I want to talk about what would go wrong if these moments were Gaussian, and if it actually came from a Gaussian random variable, because that's going to come up in our analysis in a kind of funny and indirect way, that the conditions that we'll need for the method of moments to work will be things like the moments should be different than those of a Gaussian. So you could push this sort of to higher moments, but I'll focus on just a fourth order moment. We're going to come back to this distribution a lot of times during the class, but I'm going to see it just briefly right now. So what is the multivariate normal? Well, you guys, I hope, have all seen the univariate Gaussian distribution. But just to make sure we're on the same page, the multivariate Gaussian in Rn with mean mu and covariance sigma has the following PDF. And sometimes I'll write it as n of mu sigma. And I'll put a little x in here to note that this is really the PDF. So in this case, it just takes this very sort of simple form. Some normalization, don't worry about that. But the key point is that it has the structure you expect in terms of decaying exponentially away from the mean. So whenever x is away from the mean. But you can think about the standard n-dimensional Gaussian. In the case where the covariance is the identity, and the mean is 0, let's say, then all I'm going to get is the sum of squares and the exponent. So that's exactly what would happen if I just took the coordinate-wise product of the Gaussian. But now something funny is going to happen, which is that the other sort of key fact that sometimes we'll rely on is that Gaussians are very nice in that affine change of bases for Gaussians result in other Gaussians. So if, for example, you were to take x to be sampled from some multivariate normal distribution with this mean and this covariance, then in fact, ax plus b is also a multivariate Gaussian. So what should its parameters be? So the mean is easy. I'll give you that one. So all we get for the mean is just this quantity, but does anyone know what the covariance would be of this resulting Gaussian distribution? Let me make it a bit easier. So think about where sigma is the identity. So if sigma is the identity, one of the things you can do is you can take this y variable, and if you set b equals 0 again, then you can think about what the expectation of y transpose is. Because if I tell you this is a Gaussian, then that's just computing its covariance. So any guesses on what the covariance should be? Yes. Or more generally, a sigma, A transpose, exactly. And the way to think about this is just plugging in sigma equals the identity here, and explicitly computing what the expectation of y transpose would be, and you would just get it based on this linear function. So that's one way of sort of making this intuitive. You can just take it as a fact as if you want, but if you already know that affine change of variables preserve the fact that you're a multivariate Gaussian, then it's always easy to figure out what that Gaussian should be just by explicitly computing what the mean and covariance are. But in any case, what I want to think about is what goes wrong in ICA if we had a Gaussian. So this is just corroborating my earlier claim, but the idea is that, let's take two models. So the first one we take, y equals, a times x, where a is the identity. But we can also take the model y equals a prime times x, where a prime is some orthogonal matrix. And here in both of these cases, we can think about x as being the standard multivariate normal. And then the real problem here is that y is distributed like the standard normal. I'm not changing anything. And yet in this model right here, I guess let me call it x prime here, y prime is also distributed like the standard normal, because when we plug in a prime equals this orthogonal matrix, we just get the identity again. So this is really just the statement that the standard n-dimensional Gaussian has spherical symmetries. So any orthogonal change of basis here is going to preserve exactly the same distribution. So in this case, you could never learn what the linear transformation is, except modulo what the rotation is. So you wouldn't actually be able to learn it. So this is something that goes wrong even though you have independent and identically distributed coordinates here, just because they're Gaussian coordinates. That's what goes wrong. So does this make sense? Are there any questions about this? So most of what we're going to see today is about what goes right when you're not a Gaussian. So actually what we're going to assume is that, well, let me state one more fact about Gaussians. You don't actually need to know this one, but it's good to think about what the approach is. That if x is taken from the standard Gaussian, so it's in one dimension, its mean 0 variance 1 Gaussian, then the expectation of x to the fourth is 3. And actually what we're going to assume today is that each of these xi's is strictly less than 3. You could do the same thing with strictly larger than 3. You could do the same thing if you allow some of them to be larger, some to be smaller. But it'll be much easier to think about it this way. So this is the sense in which we're going to exploit the fact that the random variables are noticeably non-Gaussian, is we're going to assume that they're non-Gaussian because of their fourth moment. You can do similar tricks for going to higher moments, but we'll try and keep it simple. Okay? Yeah.
Is there a possibility that even those non-Gaussian distributions have some sort of symmetry which still spoil the recovery somehow? How do I know that if I choose some different distribution, it doesn't have some symmetry which I also can't recover up?
So that's a good question. So actually, so the point is that, so first of all, there are a few facts that address this question. One of them is that if you match all of the moments of a Gaussian, you are a Gaussian. So whenever you're not a Gaussian, there'll be some moment that does it, as long as your moments are well defined. Now the issue is that the running time and sort of sample complexity of these algorithms, which use higher and higher moments, is going to get worse and worse the higher you go up. So you should think about what you really need in this condition is a statement that, this is noticeably less than 3. And that's something which your algorithms will depend on is, some sort of inverse Pauli bound on how far you are away from the corresponding fourth moment of the Gaussian. You could also make similar types of statements for higher order moments, but then the runtime and sample complexity gets worse. So you can think about it as you can create distributions that are close to having similar spherical symmetries, but by virtue of them not matching the moments of the Gaussian because they're not Gaussian, there'll always be some moment that shows that they're not perfectly spherically symmetric.
But can I have a distribution which has some sort of symmetry, which is like completely non-Gaussian, but still has some symmetry?
So let me answer it this way, which is so imagine I took the uniform distribution on the unit sphere for x. So that would seem bad because it does have spherical symmetry, right? But it's not going to fit into this problem because the coordinates aren't independent. So if you're independent and you're spherically symmetric, perfectly spherically symmetric, you're Gaussian. That's the point. Any other questions? But that was a very good question. All right, so so now we know at least where we have to look for where we can hope to do ICA to begin with. We have to look for non-Gaussian things, and we have to look for noticeably non-Gaussian things, and we're going to look at the fourth moments. So let's do it. So we're going to follow this approach of Fries, Jerem, and Kanan. And one of the reasons I like teaching this paper is because there's so many ways of using the method of moments. We just did an entire unit on tensor decompositions. And we're going to see other ways of using the method of moments when we talk about learning mixture models. But this is somehow a very different approach for using the method of moments because it'll be based on local search. So in a lot of cases in optimization problems we care about, when we're faced with a non-convex optimization problem, we're always worried about getting stuck in local optima and not finding the globally optimal thing. This is one example of an algorithm I know, maybe the only one, where the goal is just to find the locally optimal points. And what you're really proving is that the locally optimal points to the approach we're going to give actually recover the parameters of our model. So it's a bit funny in that way, which is the cool thing. Now, I mean, the first thing that I have to do is I have to do some of the basics, because you think about trying to learn the parameters of A and B. Well, there's some obvious things, like we'll be able to learn B, and we'll be able to learn A up to rotations. That won't involve anything new, but let me show you how you go about doing that. And where we're really going to use the higher order moments is how we learn A beyond just up to rotations. So how we can figure out A beyond just saying that we found A up to some unknown rotation. So let me just, state this part, but it should be kind of obvious. So if we take random samples from our model, what I claim is the expectation of Y is B. So finding B is easy, because you remember that in our model, we assumed that each of the x of i's was 0 in expectation. Otherwise, we pulled out the part of their expectation and put it into B, and the model stayed the same. So all I'm saying is that in this normal form, where the expectation of xi is 0, then the expectation of y, this entire part goes away, and all we have left is b. So we can estimate b very simply from our samples. We take tons of samples for y, we take the empirical average, and that'll be pretty close to b. So really, in all of this analysis, you have to carry around the errors that I don't really have b at b hat, but let's not get lost in the details. The other point is that I can also learn a up to rotation in the following approach. So if I compute this quantity, so I take whatever the true b vector is and subtract that off from y. Now the key point is that this quantity is just A transpose. Actually, let me write that, let me prove that part. This part's obvious. So part for star goes like this. We just exploit linearity of expectation. But something you may be less familiar with is that linearity of expectation works just as fine when you're multiplying by matrices. That A is not a set of random variables, and you actually can pull it out of this expectation the same way you always do. And this quantity right here, I claim, is just the identity. So can anyone tell me why it's the identity? Expectation of XX transpose? Sorry, what?
Standard normally dependent, right?
Ah, but I don't want normal, but you're on the right track. So that discussion was about why I'm dead in the water if I have normal. But you're definitely on the right track, that I need to exploit the same reasons, that it's true over there. Yep.
Like they're independent and invariance one, so the off-diagonal entries, and then means zero off-diagonal.
Yes, I've conveniently hid the answer. Right, so the point is that the coordinates are independent. So when you think about the entries of XX transpose, if you ever pick out an xi and an xj, and I is not equal to j, you know those two coordinates are independent, and you know that their expectations are 0. So you get zeros off the diagonal. And along the diagonal, all you get is expectation of xi squared, which is 1, just based on my normalization convention. So all I end up getting is I put in the identity there, so I recover A transpose. The same way that once I know B, or a good enough approximation to it, I can take samples and compute an empirical estimate for this quantity, this matrix now, which converges at an inverse Pauli rate to A transpose. But now the key point that you can sort of see is that, is there any hope of recovering A given A transpose? We have like 8 ways of seeing the answer is no right now. Right? So one is the fact that I haven't said it's non-Gaussian, so you definitely can't recover A beyond rotations, because we just said it's impossible for Gaussians. But this is the same rotation problem that we talked about with Spearman's hypothesis, that it's really the columns of A are the factors, and given summation AI transpose, you can't recover the factors just from a matrix. So there are a few different ways of thinking about why we can't recover A exactly from this. So the way that we proceeded with things like Spearman was we thought about, given access to tensors, how we can find the factors. We're going to try a different approach of making progress today. Because today our approach is, well, at this stage, all we can do is learn A up to rotation. Let's start with that and then try and learn the rotation itself through higher order moments, which is where we need to exploit the fact that it's not Gaussian. So it's a different strategy for dealing with the same type of rotation problem. Instead, we're going to deal with the rotation explicitly through higher order moments. So let me try and corroborate this claim. So there's this very important notion of the Cholesky decomposition. Which really says that if you're given some matrix M, usually the way you hear this described is that M is PSD, but another way of thinking about this is you're given some matrix M, which has the property that it can be written as AA transpose. What the Cholesky decomposition does is it finds a way to write M as the product of B transpose for some matrix B. So the way to think about this, if you guys, for those of you who know what positive semi-definite is if you're given this matrix which is PSD, you can always factorize it in a way that you prove that it's PSD. Because when you write the matrix this way, when I take a quadratic form of X transpose X on it, it's obvious that it's non-negative. So given a matrix with the promise that all quadratic forms are non-negative, you can certify that fact by factorizing it in a way that it's obvious that they are. But the real issue for the Cholesky decomposition is that these two factorizations are not necessarily the same. That's the same rotation problem, and it's the same Gaussian problem, rearing its head yet again. But in our setting, the other sort of fact that we're going to use about the Cholesky decomposition is that you can always choose B to be an n by n matrix in this decomposition. So you never need more columns than you might think. So that's sort of the key fact. So now what I want to do is I want to think about how we can use our knowledge of AA transpose to learn A up to rotation. We sort of alluded to that before, but let me make this precise through the Cholesky decomposition. All right, so the first simple claim in our setting is I claim that B is invertible. So this one is easy because, by assumption, we assume that A is invertible. So this matrix M that we get from AA transpose also has full rank. So then if you give me any other matrix where M equals B transpose, and it really is an n by n matrix, the only way that you can possibly have agreement here is if the rank of these two sides is equal. So it better be the case that B has rank n as well and is invertible. So that's not a problem. But the other point, now that I have that B is invertible, is what we can actually do is we can look at B inverse times A. That's now well defined. And what I claim is that that's orthogonal. We sort of alluded to this because the idea was that, if we applied any inner rotation inside here along with its transpose, we would preserve this identity, but we would change the matrix, which represents the factors. But now we want to prove the other direction, that that's the only symmetries we don't know about A, is just what this orthogonal matrix is. So the proof of this is also quite simple. The idea is that if we take BB transpose, we know that that's equal to AA transpose. They're both the same matrix. They're both factorizations of the same matrix. And now that we know that B is invertible, what we can do is we can pre and post multiply by B inverse and B inverse transpose. And what that gets us is the identity. So now I claim it's clear that B inverse A is orthogonal. So can anyone prove it to me? Just from this identity?
Taking the matrix physics, multiplying the matrix physics transpose.
Exactly. See, I've parenthesized it for you in the wrong way, right? You should really think about it parenthesized this way is this equals the identity, and hence this matrix times zone transpose is the identity, so it is orthogonal. So this is making it precise what we don't know about A. Because what we don't know about A is we take this matrix B, which we've found, and what we don't know is, I'm just going to call this orthogonal matrix R. We don't know R. So our remaining goal, and at some point we have to exploit the fact that it's not Gaussian, this is where the meat of the argument is we're going to exploit the fact that it's non-Gaussian to learn this orthogonal matrix. That's the point. And as I alluded to, we're going to do it through local search. So, now we get to the sort of local search part of this, the story, how we figure out this rotation matrix R. And the idea is what we're going to do is we're going to look at the following type of optimization problem. So let's see. I don't want to say this. Okay, so I'm going to define a new variable, z, which what we've learned so far is capital B. We can compute its inverse, that's fine. And we've learned little b to the expectation. Now what's nice is that this is really just samples from the following model, R times x. And the goal is to recover R. So we've reduced our ICA problem now. In full generality, we had this unknown A and we had this unknown little b. We found little b and we found something about A. So we've reduced our ICA problem to just the case where little b is 0 and A is itself an orthogonal matrix. So we've made our problem a lot simpler. And we convinced ourselves that we can't figure out any more just from second order moments. But the idea now is, what if we consider the following type of functional? So we minimize over exactly unit norm 1 vectors u the expectation of u transpose Rx to the fourth. I'm going to call this quantity, or rather, I'm going to call this quantity f of u.
To the fourth, right?
Yes. I'm calling the entire thing. So the expectation, to the fourth, everything, that's f of u. We want to try and find the minima, actually the local minima, of f of u on the unit sphere. Now that's a tricky thing, is that even though this is a convex function, we're restricting it to a non-convex domain, because we care about only things on the unit sphere, not in the unit sphere. So if you take two things, if you average them, you could end up with like the 0 vector here, which is not something we really want to consider. But when you look at the surface of the sphere, then actually it's going to have 2 times n local minima, and those will exactly be plus or minus the different rows of R, or R inverse, I forget. But that's what I want to say, is we want to, what we're going to do right now is we want to manipulate this algebraically in a way that it'll become apparent that when it's non-Gaussian, its local minima teach us something about R. Because that's the first step, is that I've just pulled this random functional out of thin air, but this will be the one that does the trick. Okay? So, the first point is that this is actually the same thing as this minimization problem. These are equivalent problems, I claim. Why?
Because R is orthogonal at the image under an orthogonal matrix of the unit spheres.
Exactly. These are just the change of basis of the same, optimization problem, is that all we're using is the fact that given some candidate solution U, we plug in this value for V. U transpose times, should it be R, not R transpose. We plug in this quantity for V, and then we get the same value. But moreover, for any value for V, we can then instead multiply by V transpose and figure out what value of U does it. So this is just a rotation of the same optimization problem. And it'll be easier to think about what the optimal solutions to this one are, and then move them back to this problem and think about how they reveal something about R. This optimization problem has nothing about R, but it'll be easier to think about what its local optima are, and then turn it into a statement about why the local optima of f of u tell us something about R. So that's our outline. So let's make that happen. I guess I don't need this anymore. So in high school, did anyone really like completing the square? Like, was anyone really excited to complete the square? No?
I liked it.
You liked it. All right. But that means you're...
Uh-oh. I don't like it anymore.
Yeah, I was never a fan. But all we're going to do is we're going to complete the square, but in a kind of clever way. And this is where the non-Gaussian part is just going to fall out from thin air. It's from completing the square. So, the first claim is that this quantity, we can rewrite it another way by just canceling the things that we definitely know are 0. So all I'm doing is I'm expanding this in the obvious way. But there are some things that definitely don't contribute just based on our assumptions. So if you think about something which, anything which has a first degree power of an xi is going to be 0, because the expectation of xi is 0. So all we're going to do is the only non-zero things, you're going to have to take the same variable 4 times, or you're going to have to take a pair of variables where you take each one twice. So that's all I'm doing. This term is obvious, and this is just if you expand this out into 4 things. When I fix I and j, there'll be 4 choose 2, which is 6, ways of choosing where I choose the I and j from. So this is all I get when I expand it out in the obvious way and delete the terms that are clearly 0. But now what we're going to do is we're going to complete the square. So the first thing is that we can rewrite this instead as summation vi to the 4th times the expectation of xi to the 4th. And then this quantity right here, remember that expectation of xi squared is 1 by assumption, so we can get rid of that term. So all we have are we have the summation I less than j, vi squared, vj squared. And what we're going to do is we're going to complete the square in the following way. Now this quantity right here, I claim is actually 2 times summation vi squared squared. 3. That's why I never liked those things, right? Because we're pulling out the 3, and then we get the singleton terms here, and then we just choose all pairs. And we have two options for which order you choose I and j. Now this quantity is easy, right? This quantity is just 3. Just because we're considering unit vectors, vi. So the entire quantity that we end up getting is, this is where the non-Gaussian is just going to fall out. I'm going to pull this term into this one. And that's our function. It's kind of magical, actually. Right? So what this is saying is this quantity, remember, we are assuming that these random variables were non-Gaussian because their moment should be strictly, their fourth moment should be strictly less than 3. So this quantity is negative, and this v is a unit vector. So, if you think about, the unit vectors, you really only have two options. You put 1 on one coordinate and 0s everywhere else, or you put 1 over root n everywhere. If you think about putting 1 over root n everywhere, then what you're going to get is you're going to raise that to the 4th power, right? So, instead you're going to get, 1 over n squared. And then when you add this up, you'll actually be better off, concentrating all the mass on one of the coordinates instead. Whichever one has the largest gap here, this is the most negative. So actually the sort of key claim, which I'm just going to assert, but it's true just from looking at this functional, is the following. Let me state it precisely. So we're only interested in v's over the unit sphere, exactly in the boundary of the unit sphere. Are only plus minus the standard basis vectors. So that's a sort of key fact that you get from this functional representation, that wherever you are, you can make progress by pushing your mass onto a coordinate which, for example, has a very negative value for expectation of xi to the 4th minus 3. So that's actually the point, is that the local optima of that problem where we're searching over v's are simple. They're the standard basis vectors, plus minus them. But this actually tells us something about our original optimization problem, because you remember we made this change of basis between v and u. So it's going to tell us the same way that the local optima of this problem are controlled, the same way the local optima of our original problem are actually going to reveal the directions in R. Right? So recall that we had the following change of variables, that u transpose R equals v transpose. So in particular, when we set u transpose equal plus or minus ei transpose, times R, we get the rows of R. So what this is really saying is that should have plugged in v equals plus minus, so then, right. All right. So if I plug in this for v, because that's where I know the local minima are, then I right multiply by r transpose, and I figure out what the solution should be for u, for where their local minima should reside. And then that tells me exactly where these local minima are. They're plus minus the rows of R transpose. So this gives us our algorithm. Is because the only thing we had to do, remember we found B, little b, then we found A up to rotations, up to this unknown rotation R, which we were only using second moments to do that, so there's no way that we could figure out what that rotation is. What we did was we used the fourth order moments now to figure out what R is. Because we defined this optimization problem, which is non-convex, but whose local minima revealed to us rows of R transpose, plus minus rows of R transpose. So that's the structure of the algorithm, which I think is very different than a lot of the algorithms you see for the method of moments, is that it really is exploiting local minima. So are there any questions about this? I can write out what the full algorithm is too, if that's helpful. Yeah?
So once you found one minima, how do you find the different one?
Yes, so the stuff that I'm not telling you about, which is also technical to analyze, is, first of all, you need to tolerate noise in all of this, and then you need to find approximate local minima. How do you even do that? So they just do some sort of gradient descent and show that it makes progress, which you need to lower bound the Hessian to say that you make progress with each step. And then we get to your question, which is, how do you actually find all of them? So actually, in the original paper, there was a bug. So the way that you could hope to do it is once you find a row of R transpose, you could restrict the orthogonal complement. Because R is an orthogonal matrix, and then you can try and do local search there. But actually, one of the annoying things is that if you think about how the error propagates, you don't actually have the real row of R. You have some good approximation. And then that orthogonal complement is just, has a very small angle with the true one. And as you project lower and lower dimensions, the error blows up badly with the dimension. So in reality, you need a lot more careful analysis of this to make sure that you can find all of them. But I'm not going to get into that in details, but that's a very good question. It can be done. That's all I'll say. Any other questions about this? I can state the algorithm if you guys prefer that, without telling you how to find the local optimum per se. So the first step is you compute an approximation to expectation of y is b. Then you compute this covariance matrix. We remove the B term, but you essentially look at y transpose, and you know that that quantity is some matrix M, which is AA transpose, and you apply Cholesky to write M as B transpose, where B is an n by n matrix, which you can do. And then there's this critical step, which really takes a lot more work to do, is you find all the local minima of this functional f of u that we described. It's just the expectation of u transpose times the inverse y minus little b to the fourth. And you let these solutions be plus or minus the rows of Ri transpose. Now, the important point is when you find these local minima, you're always going to find them in a paired way. You're actually going to find 2n things, because you're going to find a row of R transpose, and then you're going to find minus that row as well. They'll always come in pairs this way. And in this way, you can just choose which one to be positive, which one to be minus that you want. It doesn't matter. And then you could form them into the matrix. So you're taking one representative from every pair. It doesn't matter which one. You construct this matrix R transpose. And then, indeed, what you finally do is you set A equals B times R. Because remember that B inverse times A was the rotation matrix that we're looking for. So this was the algorithm. Modulo this step, which I didn't really tell you much about other than that you can do it through gradient descent and through analyzing the Hessian of all of this stuff. So it gets quite messy. Any questions about this algorithm? So this is a very different way to use method of moments. So what's also funny is that there's actually a way to do this through, you can think about similar types of approaches about being non-Gaussian. So you remember for our assumptions, I still have it here, that we assumed that the expectation of xi to the fourth is strictly less than 3. You can even make all of this work even if you just have expectation of xi is bounded away from 3. Could be larger or smaller, and it could be, whether it's larger or smaller, it could change from coordinate to coordinate. It doesn't really matter. All that changes in that algorithm, instead of just thinking about the local minima, you also have to consider the local maximum. So it doesn't really change anything. But does anyone know what it's called when you subtract the 3 from both sides and you look at expectation of xi to the fourth minus 3? So I can also think about this as I'm really analyzing expectation of xi to the fourth minus 3 times the expectation of xi squared squared. Just because this is 1 in our case. Does anyone know what this is?
Kurtosis.
Yes? Does anyone know what the next one is called too? It's in a family. It's kurtosis. But this is also the fourth cumulant. So there's a funny way of thinking about this method of moments, as what it's doing is it's reparameterizing the moments in a way that you can define the same way that you have the standard moments. You can look at the standard cumulants, and the Gaussian has the property that after its second cumulant, all of its other cumulants are 0. And it's the only distribution which has that property. That's what we were exploiting, was that the fourth cumulant is non-zero, and then we got our algorithms to work. The same way there's a way to do this with any other higher order cumulant. But there's also a way to think about how cumulants get used in tensor decompositions. So I can actually give you the idea of how you could do the same type of algorithm through tensor decompositions, which I'm just going to sketch this part because it's a little bit complicated to see, but let me tell you the basic idea. Maybe I'll give you guys some homework problems on cumulants to give you guys some practice with them. I think they should be better known. All right, so let's try to use tensor decompositions for ICA. So I just said that there's this crazy, local search approach on the fourth order, really cumulant, that works in finding this and solving this ICA problem, and that there are higher order versions of it. But let's try and think about just the fourth order one, whether we can do it through tensor decompositions or not. So, one of the natural things to do is to construct a fourth order tensor to begin with, which hopefully has some nice structure. I'm always just going to subtract b because it's just kind of a nuisance that I don't really want to deal with it. So I'm really getting samples from a times x. And what if I take whatever that vector is, and I take its outer product with itself 4 times? So I get a fourth order tensor, and then I look at that expectation as I choose x's in such a way that the xi coordinates are independent. So this I claim, and you should try and convince yourself of this fact, because I think, using linearity of expectation in the context of matrices and tensors takes a little bit to wrap your head around to convince you that everything I'm doing is actually kosher, but it is. So what I claim is the following. Is that it actually has this type of structure. So if you think about it this way, of like this forms a fourth order tensor, and I think about one of the entries in this fourth order tensor, one of the things you can do is just convince yourself that I create the same entry on these 2 different sides. That's a much easier way of thinking about it, because when I pick out some row in the first dimension, some row here, some row here, some row here, and I look at this entry in that corresponding 4 tuple of coordinates, well, the same way it'll pick out those entries in here, and then just multiply it by this quantity. So I'm just pulling out the linear term that multiplies everything. And then you can also think about what that looks like, not just looking at individual 4 tuples of these 2 tensors, but convince yourself that it really does have this structure. So now, one of the complications in trying to use tensor decompositions is that this object right here is really a fourth order tensor in its own right. Because for every tuple, I, j, k, and l, what does it do? It assigns this value to it. I, j, k, and l can be repeated indices if you want. So I claim that this tensor actually has a fairly nice structure, but it's not as nice as we would want. So one of the first things to think about is that what I claim is that d I is just expectation of xi to the 4th. So we definitely have non-zeros along the diagonal of this tensor, but we also have other non-zeros along in this tensor too. So where would the other non-zeros be?
This product of squares.
Yes, exactly. So for example, also dijj would just be the expectation of xi squared times the expectation of xj squared. And why does it factor this way? Because the xi and j are independent. So we just get this. And the same way, it's also true if you took, you know, I, j, j, I, or I, j, I, j. So what ends up happening is that we have, you know, if this tensor had only non-zeros along the diagonal, this would actually be a low-ranked tensor in our usual sense. Because all you would pick up would be things like AI, tensor AI, tensor AI, tensor AI, and you would have low rank. But you have all of these off-diagonal terms that actually make it not as nice a tensor to deal with. But there's a trick that you can actually look at other statistics that you can compute that you can essentially remove the non-zero off-diagonal entries. So there's a way in which the way that you do that is through cumulants, which is the same way that it came out of completing sum of squares. So all of these techniques are really just the same thing. There's even a way to interpret it as matchings in a graph because those give you moments of Gaussians. But let me show you the basic idea without getting too lost in the details. So this is something which I can measure from my samples. You know, I know B, and I just compute this, and I take the empirical average, and it converges to this expectation. But what's something else that I can compute, which can be useful in removing the non-zero off-diagonals, is we could also do something like this. So we can let y and y prime be independent samples. Then I could compute this expectation. Or what I'm doing is I'm plugging in y for the first two and y prime for the other two, and those are independent. So this, the same way, what's going to happen is that if you do the same tensor math, same thing happens, but now our inner term corresponds to two different random variables. When you look at the tuple, you know, in this of I, j, k, and l, the first two come from the first sample, the second two come from the second sample. So let me call this tensor the same way, d super 1. So what should the I entry of this guy be in our model?
So 1.
Yes, 1, right? Because now these two sets of random variables are independent. So I just get expectation of xi squared times expectation x prime I squared, and I get 1. What about, let's make it more interesting. Well, all right, I'm just going to quiz you, so it'll be like a game show for the rest of the time, and then we'll see if this works. What about IIJJ? 1? Not all the answers are 1. All right, IJ. 0. I told you there'd be things that are not 1. Right? And then the last one that we should care about is this guy, which 0. So now I can tell you what the strategy is, right? This is also something we can compute from the data. Now what happens is when we subtract these two guys, we're subtracting 1 from the diagonal. So we had expectation of xi to the 4th. We're going to pull 1 out, and we're going to kill some of the non-zero off diagonals. In this case, all we do is we kill the first one, which is iijj. But we don't kill any of the others. So what can we do to kill the others? So what's the strategy? We can just flip how we do this, right? Instead, I could do y minus b, y prime minus b, y prime minus b, y minus b. That'll also pull out a 1 here, and it'll have a 1 here, and it'll have zeros here. Or what I can do is I can do, y, y prime, y prime. I'm going to pull out the 1 here, 0, 1, 0. So in this way, when I subtract off, what happens is I kill all of the non-zero off diagonals. And what I'm doing is I'm essentially completing the square through tensors, because these guys go to 0 when I do my sort of multilinear tensor algebra. And I'm subtracting off the same 3 here, because I've done it 3 ways. And that actually is the cumulant, yet again, which then would give me a tensor, which I can compute just as, this quantity minus the 3 other quantities, and I can compute an expectation of that. But that really would be a low-rank tensor, because I've made it so that that inner term only has non-zeros along the diagonal. So there's actually another way to do this through completing the squares through tensors. Yeah?
Doesn't this tensor already have low enough rank that we could compute it? Because when we have order 4 tensor, we can do rank up to n squared, right?
Yes. So there'll be an issue about the independence of the factors, I think. But that's a good question. Let me think a little bit more about that. But I don't think you can do it simpler than this. I'll think about it, though. There's also a sense in which what's really going on underneath is matchings. So I said that the 4th order moment for a Gaussian is 3. That really comes from the fact that if you have 4 nodes, there are 3 distinct matchings. And each time we're doing here, when we choose, some way of choosing where the y and y primes are, there are some matchings that, we respect, which these would be the ones which respect the sort of division between where the 2 random variables came, and the other ones have 0 contribution. So what we're really doing is we're covering that graph with matchings, and that's the sense in which we're diagonalizing this inner decomposition. So what I might give you on the homework is that there's a way to do all of this abstractly, just knowing that a cumulant exists, but not actually doing any computations, that it has to diagonalize the thing. So there's a way to do this without any mess, but through generating functions. So that's a new thing, so maybe I'll test it out on you guys, and you guys can be my guinea pigs. But I think that's about all I have to say about this. So I guess we'll end a bit early. And also, so what I was planning on doing, so we have one more class before before spring break. So what I was planning on doing was doing another discussion day. Did you guys like the first discussion day? How can I get you guys more involved in talking about stuff? So the discussion day that I'd originally planned for going after the tensor unit is to understand what are called semi-random models. So those are models in which you have sort of an element of average case, where there's some distributional model generating the things you want to do. And then there's also an adversary who can sort of mess up the distribution a bit. So there are a lot of settings which allow you to sort of test how rigid your distributional assumptions are. See, for all these tensor decompositions, we're using conditional independence to do things. In some cases, that can be a very strong condition. In other cases, it's not that bad. So for example, independent component analysis is actually a huge field. And they were some of the first to really use cumulants algorithmically. But since then, cumulants and going to higher order moments can be somewhat not robust outliers. So after that, they started to use other notions of independence. Like they try and look for linear transformations, which minimize the mutual information between random variables. The trouble is that those problems then, instead of having provable guarantees, they have no provable guarantees. So it's very tricky to sort of talk about some of those things. But as a community, they're looking towards those techniques because they seem to be much more robust, even though they're heuristics, than using higher order moments. So it's sort of an interesting thing to think about is, the types of things we talked about, which of them are or aren't robust to distributional assumptions. And there are cool models in between average case and worst case for trying to probe these things. So one of the ones which I wanted to discuss was semi-random. We may at some point talk about like smooth analysis, another way to think about things in between the two. But if you guys want to do another discussion day, I need you guys to actually read the paper and discuss it, right? And be interactive. So more homework all around? Read the paper. No?
Is the paper on the website?
Yes. It's an old paper by Feige and Killian. So, I mean, you don't have to understand like all the technical details, but you should understand enough of what they're doing for the high-level approach that you can talk about what makes it different than other techniques. So more homework all around? All right, more homework. All right, so I'll send out an email with which sections of the paper I want you guys to look at. It won't be the whole thing, and it's a short paper anyways, but I want you to understand what makes a semi-random model tick. And think about how it connects to things you care about.
Anchor, quick question. I forget if you said anything about it, but do the empirical errors matter? Like from the, I was
all
just
of the stuff here can be done with polynomial sample complexity, and then you have to carry around this error term and show that the error term decays at a polynomial rate with your number of samples. But the usual way, you depend on the condition number of A, you depend on how far you are away from 3 for these moments, and then you use those things to prove lower bounds in the Hessian, and then to carry your error term through. So the entire thing is kind of a pain, and I mean the first rendition of this, there absolutely was a bug in carrying the error through, but it can be done. So I think the right analysis from a later paper.
So it's not like conceptually like enlightening. That's kind of why we're skipping it.
Yeah. I mean, it's the type of thing which
it's important, but not.
I mean,
conceptually.
So the problem is like I could do it if I wanted to, if I had to prove it for a paper, but then I wouldn't remember it myself because it would just be something you do.
That makes sense.
I mean, it's not like a tight analysis; it's just an analysis. So if it was the right one, I might be more inclined to show it to you, but it's something.
This might be a stupid question, but why are you not doing
Are you going to
Yeah.
Okay.
What do you mean by small?
Well, I just wasn't here last week, so
No, right.
Oh, but so the issue is that
Okay.
so
You don't have the link to the
X
YouTube
were
stuff?
I can email you.
Yeah.
Awesome. Cool. Did he head back to
Plus
pizza?
minus 1
No,
random variable.
I didn't.
I just was interviewing.
If you do
so-
30
No, that makes
points,
sense. Yeah, no worries.
Cool.
Yeah,
Thanks so much.
yeah.
because
Just send me.
everything is
Yeah, send you an email.
Yeah. It'd be good if I
the
could send that
expectation
email
of
to the
that
whole
side of the
class.
third is also 0.
That's true.
I'll try to convince him to
And
do
that would be
it.
bad.
Yeah.
So you'd have a low rank tensor, but because the tensor is 0.
Bye, Mike.
That would be bad, right? Yep.
I just want to make sure that obviously
Right. Are you uploading the video?
All of the videos are online.
No.
You go to YouTube. They've been up
No.
for like
No.
a while.
You just
now.
need that
Oh, I
they're
didn't know.
all
Oh.
bounded away.
I'll tell
from
Anchor to
3
send the email because it's
by
like,
some.
Okay, I can just search for them.
And these algorithms will
You're
depend
welcome.
inverse polynomially on what that something is.
I see.
So if this is if you have this is true for all I, then you're going to have some poly dependence on 1 over delta. So if you carry it through, that's where it sort of shows up.
Alright.
So if you think about it with this function, right? I may have erased it. So we have this functional, which I guess you can still make out on the board, which was this thing, right? So this was the thing, right? So if you think about if this is exponentially close to 3, you know, if it's 3 minus 1 over 2 to the minus, 2 to the n or something, then you'd be in trouble because this guy is negative. So it is a local optimum when you put all of the mass there, but barely, it's something where if I gave you noisy access to this quantity, then the amount, the fact that it's a local optimum would be sort of swamped by the
talked about
noise
K-median
and the sampling. So the smaller this quantity is, the zero
I think so.
magnitude, the sharper and sharper bounds you need on how close your empirical averages are to the true thing to actually be able to tell that it is a local optimum. That's what I'm saying. So if this were like 3 minus 1 over 2 to the n, then if I just gave you noisy access to this function, that wouldn't be enough because that tiny term would get swamped by sort of sampling. So that's the point. Yeah.
Is it possible, like, for example, we are doing minimization, right? So is it, A7 is possible, like, have a classification vector and negative one?
Oh, yeah.
So do we, in the average, do we like need to check, for example, given a y and x, you need to like check this two numbers to like correct?
No, because so the point is, so what's going to happen is this local optimum, I'll have plus, in this one I'll have plus EI and minus EI. And in the original one, I'm going to have plus a row of R transpose and minus a row of R transpose. So I'll get 2 times n local optimum, but I'll be able to look at them and pair up and see which ones are plus minus of each other. And then the point is that in this model, actually, so the way that we constructed A at the end of the day was as, B times R. So if you think about what it means to flip the sign of a row of R, that's the same thing as flipping xi. So if I change the sign of a row in R, which is what happens when I change the sign of a row in R transpose, right?
Okay.
Then what happens is I'm verbatim just flipping the sign of xi, which I can never learn, the sign anyways. Like if the distribution has expectation 0, I could always flip it.
Oh, yeah.
So the point is that that's a good question, but
you can never learn that information.
Exactly. So the point is that the things that I don't learn about it, such as the order of the R's and their sign flip, are never things I could learn anyways, because whatever model you give me, if you give me any permutation and sign flip, I can construct a new model which has that, which exactly matches as a distribution.
Okay.
So you're still learning up to the symmetries of the model.
Okay. Thank you very much.
Yep.
Uh-huh. You mentioned that for those methods matching cumulants, going to be more robust than matching moments?
No, as in they're both, cumulants I think are a bit more robust than moments, but in general the ICA community has entirely gone away from cumulants.
So what
They use heuristics. It's kind of disappointing that all this stuff was back in like the 80s, where they were the first people to use cumulants, I think. And they had these things which they didn't even state they were provable algorithms, but they basically were provable algorithms. So like Friese, Jerem, and Canaan, A, there's a bug in their paper, which is kind of obnoxious. B, the proofs people had for ICA were basically correct. They just didn't have a sample complexity analysis, but you can make their stuff work. So, the thing that was missing.
Yeah, in the end, the matching cumulants are essentially still matching moments, right?
Yeah, exactly. Exactly, because the cumulants are a different basis for the moments. So there's a sense in which, you could hope that, so cumulants are sometimes used in statistics to control the, to control the shape and also control the tails. where you have bounds on the growth rate of cumulants, sometimes that can be more powerful than having comparable bounds on the moments, just because the sort of cumulants capture more the notion of like sums of independent random variables. But the caveat is that even though ICA, like the community, developed all these cumulant things, at some point they decided these things aren't robust outliers because they're taking the fourth moment. And meanwhile, theorists have gone and looked at higher order moments like eighth and so on.
So if sample complexity is not an issue, you should be like going to higher and higher order of cumulants and moments to match.
Yes,
So
yes, but also model misspecification. So, if it's not really independent,
Yeah.
But there's some fraction of things which are sort of noisy, then the higher order moments become much more sensitive to the model misspecification. So it's more like, instead of looking for a linear transformation where, cumulants are as small as they could be for those random variables is sort of the optimization problem they're doing. They're looking for which linear transformation minimizes the mutual information between pairs. If you could do that, it would be really robust to model misspecification in the same way that, like, when you do maximum likelihood, it's going to converge to the closest in KL divergence. There's still sort of information theoretic ways to justify some of the things they're doing, that if you could solve those problems, they would be, much more robust to model misspecification.
So one thing we looked at and got stuck with is for Gaussian mixtures.
Yeah.
I'm not sure if Sean mentioned this to you. It's like, so first one we read the Fourier paper by Van Pella.
Yep.
We thought like the same thing, but then in the end, they indeed calculate the generating function, but all the information they use about generating function is their derivative at 0, which end up with the to be the cumulants, right?
Yes.
In the end, they're just matching the derivative at 0, which are matching the cumulants.
Exactly. Yep.
But instead, we're saying like, if can we directly match the generating function of Gaussian mixtures, because we know they are of very pretty form. Because so think of like this, and then X is a Gaussian mixture, and then you're getting.
But you could also try and think about matching the cumulants of a Gaussian.
But then in that sense, I think Van Pella had the paper on applying the matching cumulants for Gaussian mixtures. It has to go up to order k. That leads to exponential in k complexity everywhere. So what we want is that can we say for some nice cases we can get rid of this exponential dependence
For over complete ICA. Or what?
Yes. No, for Gaussian mixtures, right?
But you guys already did that, right?
That has to be very that has to be high dimension. So, but it should be the case that.
Oh, I see. So there's this issue of like how the dimension relates to the number of components.
Yes, that I.
So you need D to be at least some poly in K.
Yes.
But you could hope that D is.
For example, this should be an easy case.
Yeah.
Like
you could hope that you could even handle D as any poly in K, like K to the 0.1.
Yes.
Provided it's in smooth.
Yes. So the observation is that if you consider the X and X is the mixture Gaussian, then it's just a mixture of exponential X sigma X minus here plus U prime X and different components. Then it is saying that, but here for this generating function, you can evaluate at any S. So it's saying that can we match this generating function as if we are matching the smooth density function?
I see.
Because if we, bottom line is that you can evaluate.
But you're going to need to match. So I mean, there's also the question of you're going to need to match derivatives of it.
No, just directly.
No, I'm saying to do the like D equals K to the 0.1. I think you can use the power of match as your range over S, but you may also need to match derivatives.
Yeah, but
not necessarily at 0.
Mm-hmm.
But you definitely need higher order derivatives.
Why?
To.
Because you see, you can take as many sample points of S as you like. For the simplest case, if mu is 0, like they are all centered at 0 point, and
my intuition is you have to take derivatives to get algebraically independent things.
Look at this. So if they are all centered at 0, and let's first consider if it's one-dimensional. Okay. So it's just like 0-centered Gaussian mixtures. Then you get rid of this term, and this is x. You take expectation over x. So this is you're getting this, and what you can do is like you could take s to be I times integers. So here you can estimate.
So you're taking the Fourier transform of it, right?
Yes, but like square root of n. So you can estimate any of these moment generating function with very low sample complexity because they're bounded, right?
Right. Yeah.
So, but look at this. You will get like summation of exponential of like what I remember is that you will get the mixture of trigonometric series. Yeah. Right. Yeah. And you know how to do that. You wrote the book.
Yeah, I know how to
and
do that.
You know it's stable, right? In the
Yes.
sense. It's stable in terms of.
You've read that paper. All right. Yeah.
So this is just one simple observation of like how you can possibly.
So this was actually some of the stuff that got me interested in like number theory. Is like these are number theoretic questions. Is because they're about how algebraically independent are sets of trigonometric polynomials.
Yeah.
All right, interesting question. Let me think about that.
But we got stuck here because we don't know if you add this
You're adding a decay term, which is is that the issue or? So what's the issue with adding the mu?
If you add the mu, here we can take s to the square root of n, and then we get a series of trigonometric series. Mixture of trigonometric series. But once we add mu, because mu we only multiply s once, and here it's exponential quadratic thing. We don't know how to evaluate where to take the sample points of s for this generating function to do the matching, so that we can get some algebraic tricks to solve this matching thing. So one guess is that we can.
And this is mu sub I, right? I mean, it's like
mixture of exponential quadratic.
I see.
Like one thing is like if we consider the common covariance case, then we guess this single variable and just try to play around with the mean. Right. Then that so if we.
But that's doable, right?
I think so.
Yeah. I see. It's the issue that you have a quadratic and a linear term, which both have unknown.
Yes. But so we will.